Hey guys, we're back at it again. My name's Brandon. This is Chemistry 361. This is our video assignment number 3. Today we're going to be talking about H1 NMR, C13 NMR, and mass spec of a specific pharmaceutical compound. If you remember my last video, we talked about phenofibrate. We talked about its IR, its skeletal structure, and the functional groups and the frequencies within those functional groups in its IR spectrum. I'm not going to be going over that again. You can always review that video later if you'd like to. But today, like I said, we're going to be talking about phenofibrate and its H1 NMR interpretation, its C13 interpretation, and its mass spec. I have a few diagrams up here on a board. I'm going to flip it over. I'm going to be highlighting a few things as we go along. All right, here we go. So if we're looking at this again, once again, this is our skeletal structure of phenofibrate. We've gone over that before, so I'm not going to go into detail with that. Below, we see a graph, and this chart, I should say, is the H1 NMR spectral analysis of our compound. Basically, what that means is it is understanding that hydrogens are giving off signals in our compound, and when it gives off signals, it also tells us where and when, at what points those hydrogens can break off. So if we're looking at it here, we see a signal right here. This is a tall peak. We got another one over here. We have a few more right around this area. ppm stands for parts per million. But like I said, these signals are letting us know where the hydrogens are breaking off. So right here, if we're looking at this one's, I would say it's right around 1.6. It's just past 1.5. It's right around 1.6. So if we go back up here into our skeletal structure, we see that these hydrogens off these carbons, these are CH3s off these carbons, they are giving off that same signal. So we know that this peak is designated to these hydrogens breaking off. And from that, we can determine functional groups as well. If we come up here, I also want to show you these words, singlet, doublet, triplet. That's letting us know the environment of the hydrogens adjacent to other hydrogens. So if it's a singlet, it's not going to have any hydrogens next to it. If it's a doublet, it will have one adjacent to it. And if it's a triplet, like in a CH3 bond, we can see 3 hydrogens adjacent to one another. All right, so now I'm going to drop down here. As I drop down here, this is our C13 NMR spectrum. This is dealing more with carbon signals instead of hydrogen signals. So we notice we have a lot more peaks here, a lot more signals given off at different locations. Once again, these numbers, these ppm, these parts per million, are designating where those carbons are that are being broken off. So if we're going to look at this ketone right here, if we're going to look at this ketone right up in between the 2 aromatic rings, it's giving off a signal of 194.3. So if we go back down into our chart, we notice right over here that there is a signal given off at 194.3-ish. I like to say ish because I cannot determine based between those two numbers, 180 and 200, that is exactly where it is. But judging by my diagram up here, we can make an educated guess that that's exactly what we're dealing with. So this is the signal that this carbon is giving off. And these carbons are all designated throughout the entire spectrum. And that is exactly what we're kind of dealing with. We're dealing with signals being given off by the carbons, signals given off by the hydrogens in these H1 NMR and the C13 NMR spectrums. The last thing I'm going to talk about is mass spec. So if we come over here, this is our mass spec. And basically what mass spec is all talking about are the certain types of ions that we'll see and their masses related to them. So let's first talk about relative abundance. These numbers are the relative abundance to it. It's more of a percentage, and that's dealing with how often we see these types of ions, these types of compounds in nature, in the environment. If you notice this tall peak right here, it's labeled at 233.06, this tall peak. We also give it the M plus dot. That is the base abundance, base peak abundance. It's the most abundant ion that we see in nature of phenofibrate, of C20H21, C20H21ClO4. All of these other peaks right here that we see, 273.04, 318.97, 360.99, all of these other little peaks that we see coming along here. These are different peaks that are located in nature, and it is given its relative abundance. So if we're looking at 318 and we come over here, we see that 318 is kind of around, I know that's a little zigzaggy, but kind of around 18 to 20%. That is saying to after specific functional groups have broken off of that ion, how relatively abundant it is in nature. So once again, this is mass spec, and that's dealing with the ions abundant in nature and its relative abundance in nature. Once again, all of these things that we've talked about today, HNMR, C13 NMR, mass spec, this is all dealing with different signals that we're giving off in the masses that we deal with in the ions that we see in nature. I hope this helped you guys out, and I look forward to talking to you guys again.